Hi, welcome to another video tutorial. In this video tutorial I'm going to go through an example of Huffman coding. And what Huffman coding is an algorithm to compress a piece of text or other data so that it takes less space in memory. And the Huffman coding algorithm for compressing data uses something called a Huffman tree. And I'm going to show you what one of those is with an example. So, my example is going to be that I want to compress the text hello world. Okay, so hello world. And what we've first got to do is we've got to look at the characters in hello world and see how frequently they occur in a text. So I'm going to do a little table over here. So the first character we've got is L. And I'm doing this in frequency order. So we can see here that L is the most frequent character in this text because we've got 1, 2, 3 L's. The next most frequent character is O, and that's because we've got 2 O's in the text. And all of the other characters there is just one of, so I'm going to write those in, and it doesn't matter which order I put those in my table. Okay, so those are all the characters which go into making up the text hello world. And you'll notice here that I've got this space character here, and that's because where we've got a space in our text, that is stored as a character in memory as well, and there'll be an ASCII code for that if you were, for example, encoding your text in ASCII. So we've got to include that in our running through of the Huffman coding algorithm as well. So what is the process of creating this Huffman tree then? So to find out what our Huffman code is, and which is going to be in total take up less bits than ASCII, I'm going to be comparing it to how many bits the same text would take up in ASCII at the end. We've got to construct a Huffman tree, and that will allow us to work out the Huffman code for each character. So how do I do that? Well, what I've got to do is look at each character here and put them in frequency order, going from lowest at the top to highest at the bottom of a list of nodes, and these are going to be the nodes in our tree. So I'll just do that now. So we're going to abbreviate space to SP, which will save a bit of time. Okay, so those are my nodes, and those are going to form my Huffman tree. And you can see in each node I've got a number representing the number of times that character occurs in our text, and I've got the actual character in there, and I've abbreviated space to SP. So what is the first part of our algorithm then? So first of all, what we've got to do, and we'll put a line down there because that's step 1 of our algorithm there, to create those nodes. And the next step is to take the top 2 nodes and add the frequency of the characters together, and then slot that back into the list of nodes so that it is still in order. And I'm going to show you what I mean by that now. So what I've done is I've taken the top 2 nodes, so in step 1 that was space and D, and they both occur once in our string of text. So I've added the number of occurrences together, so I get 2. Then what I've done is created a new node with just 2 in it, and slotted that new node back into the list of nodes that we've got, so that it's in order still. So we've got our 1s, 2s, and 3s value of occurrences. And then I've taken 2 lines out here and attached the space and D to the end nodes to the end of here. So you can start to see that this is how we're going to build up our tree. So we're going to repeat that process until we've only got 1 root node and we've got a tree expanding out. So I'm going to show you the steps of how to do that now. Okay, so this is the next step of our algorithm. So you can see what I've done here is done exactly the same as I did from step 1 to step 2 here. I've taken the top 2 nodes, in this case from step 2 it was R and W, and I've added the frequencies together to get 2, and I've slotted that back in to the list of nodes so that it runs in order. And I've got, branching off of my new 2 node, I've got the original nodes that I made this 2 node out of in terms of the frequencies, and we've then got to repeat that again once more for this E and H. Okay, so this is the next step of our algorithm. You can see I've done the same thing with E and H. I've got a new node which is 2, and I've put it in to the correct place in the list. So we've got 2, 2, 2, 2, 3 now as our list of nodes. And branching off of these, we've got the original nodes that we had in the list, which have a frequency of 1. So this is how we start to build our Huffman tree. And in the next step, what we're going to do is combine these 2 top nodes to create one with 4, and I'll show you what that looks like in a minute. So you can see again, I'm just repeating that process. I'm adding the frequencies of the top 2 nodes, and I get 4 as my frequency if I add these 2 frequencies together. And then I'm just constructing a tree from those 2 nodes there. So I'm branching off the node with a frequency of 4, and having these 2 parts of the tree branching off of there. So I continue to do this with these top 2 nodes here. So I'll get another 4. Okay, so this is what my what the algorithm looks like after the next step. So what I've done is I've combined these 2, the node with O in, so there's 2 occurrences of O, so it's a node with 2 and O in, and this node with a frequency of 2 here, to get another node with a frequency of 4, put that into the list so that the list is still in order. So we've got a node with 3 and our other node with 4, and it's in numerical order still. And then what I do next is repeat this and take the top 2 nodes, so 4 and 3, add them together, and then I'm going to get a node with 7. Okay, so that's the next step. If you look here, I've got my node with a frequency of 7, which is made up of this node with a frequency of 3, which is representing the character L in our text. And this node of frequency 4, which is representing these 2 nodes, and so on. And we've got almost our complete Huffman tree. We just need to combine these 2 nodes to get a single root node. And if I combine these 2 nodes, I'm going to get a node with a frequency of 11. Okay, so this is our final complete Huffman tree. But it's not quite finished yet, because what we've got to do is, in order to create a binary code to represent our characters, what we've got to do is label each branch going upwards as 1 and each branch going downwards as 0. What this allows us to do is it allows us to create a code to represent each of the characters. And I'm going to do that here now. And the way I'm going to do that is, for example, if I wanted to find out what the Huffman code for the character L was, I would go along the, I would trace along the branches of the tree. So go along here, and that's a 0, and along here, and that's a 1, until I get to the node with the character L in. So the Huffman code for the character L is going to be 0, 1. Okay, so from the Huffman tree that I showed you a minute ago, and I showed you how to construct, I've come up with this Huffman code. And if I was to represent the text hello world in 7-bit ASCII, I would need 7 bits to represent each character, and there's 11 characters, so I would do 7 times 11 to work out there would be 77 bits to represent hello world. But with my Huffman code, what I could do is I can add up how many occurrences and how many bits each character it would be in my Huffman code. So for example, if I wanted to work out how many bits the L's are going to take up, I would do 3 times the number of bits each L takes up, and that would be 3 times 2, so I get 6 for L's. Do that for each row, and the total you would get is 32 bits. So we only need 32 bits to store the Huffman code. So that's a 45-bit reduction in the number of bits that we need to store it compared with 7-bit ASCII, or a 58.4% reduction in space required. But that's ignoring the space required to store the Huffman tree, because you would need to store the Huffman tree in order to decode a Huffman code. To decode something in Huffman code, let's have a look back at our Huffman tree. So for decoding, looking at our Huffman tree, if we want to decode an L, we would look at the Huffman code starting at the root node. See that it starts with a 0, so we go down the branch of the tree with a 0. See that the next bit is a 1, so we go up the branch of the tree with a 1, and we come to a node with no further branches, and we see that it's an L. So and that's how you decode Huffman code. You simply traverse the tree using the code that you want to decode, until you come to a node with no further branches coming off it, and you know that code is representing that particular character. Okay, so I'm just going to go over some of the key points about Huffman coding that you'll need to be aware of. So you need to know that Huffman coding is a lossless compression algorithm. And so basically all that means is that the data, the compressed form of the data, we don't lose any information about our original data in the compressed form of the data. So I can decode I can decompress the compressed form of the data, and it will be exactly the same as the original, because I still have I'm still representing the entirety of the original data in the compressed form. And as I've written there, the algorithm will always perform at least as well as fixed length encoding if you ignore the space needed to store the tree. The Huffman tree that is what I'm referring to there. And what that essentially means is that the Huffman coding representation of the data is never going to be larger than the original data minus the space that the Huffman tree takes up. And a final point about the example that I showed you: if you used a longer string of text, the Huffman coding would likely perform much better, because the regularity of the characters becomes more pronounced. So the benefit of having a smaller representation for more frequent characters becomes more effective at reducing the number of bits that the compressed form will take up. Okay, so I hope you found this video on Huffman coding useful. Thanks for watching.